Hey students, let's continue class 12 on linear algebra and differential equation. Today we will start the differential equation part of the course, especially the first order differential equation. This differential equation is very important. It's applicable in different disciplines, including in sciences, engineering, and mathematics. That's why you are supposed to take this course. So differential equations, everywhere it says a differential equation is like, when you say differential, it is derivative to me. No? This differential means derivative. Derivative. So it's like differential equation is any equation that involves one or more derivatives, as I told you, of an unknown function. For example, here we have second order derivative, here we have first order derivative, here we have a function y. So this equation consists of what? Consists of one or more derivatives. This is like we have two derivatives here, therefore this can be treated as differential equation. And again, here we have ds by dt, which is the derivative of s with respect to t, is given as simply sum e raised 3t times s minus 1. So here we have a derivative. Therefore, this is also considered as what? A differential equation. So differential equation of this type, that is 1.11, we have like the unknown is like x to mean. We have like the dependent and independent variable. In this case, y is dependent. Y is dependent on x. And of course, x is like independent. And here in the second equation, s is dependent on t to mean, which is like s is dependent, and of course, t is independent. So like differential equations such as this was 1.11 and 1.12, in which the unknown functions depends only a single variable. For example, this is dependent on a single variable x, and this one is also dependent on a single variable t. And such differential equations are called ODE, which means ordinary differential equation like this. There are of another type called PDE, that is the partial differential equation, that we are going to see it now. The PDE, this is the PDE, okay? And a PDE means like the derivative, I mean the differential equation is dependent on two or more independent variables. For example, see, this one is called the Laplace equation, and the Laplace equation is like dependent on the variables x and y. As you can see, it here is like the second partial of u with respect to x, and here we have the second partial of u with respect to y, which means we have the function u, which is like dependent on x and y, And for this reason, when we are going to differentiate u, just maybe you will be asked u with respect to what? Maybe with respect to x or with respect to y. Okay, so maybe we can also go to the second partial of u with respect to x, or we can also go the second partial of u with respect to y, or maybe we can take the second partial of u with respect to x with respect to y. So as you can see that u, which is a dependent variable, is dependent on two independent variables x and y, and such type of differential equation is simply called the partial differential equation. And like one way in which differential equation can be categorized is by the order of the derivative, or the highest derivative, we can say, that occurs in the differential equation. For example, if you go back here, the highest derivative is 2, therefore this is called what? Order 2, ODE. Order 2, ordinary differential equation. And this one is the highest derivative. What we have is first derivative So this will be order 1, we can say. Here also the partial derivative could also be like treated as order 2. So differential equation can also be treated or like characterized by its highest derivative, and the highest derivative is simply called the order of the differential equation. How are you going to model differential equation? Like formulation of differential equation, better to say formulation of differential equations, DE. Just how are the differential equations formulated or being formulated? So let's we have this common one, that is the population model. The population model, such as the Malthusian model for the growth of the population of bacteria, assumes that the rate at which, the rate means what? Always, please, you have to understand the rate. The rate is like the derivative of a certain function with respect to t, okay? Rate is simply the derivative of a certain function with respect to time, okay? Rate represents for the time, okay? Assume that the rate at which the culture grows is proportional to the number of bacteria present at that time. If PT, P at time t, denotes the number of bacteria in the culture, which is at time t, then this growth model is described mathematically by the first ordinary differential equation, because we have said that the rate at which the culture grows, that is dP by dt, is simply proportional to the population P. So just like if you remember, the proportion is like written here, which is proportion to P. But in order to avoid this symbol, we can use what? dP by dt is equal with some constant times of P. That's why we are coming here. So where K is constant, since the culture grows in time, K is positive to mean. Here, the unknown function is simply P of t, that is the number of bacteria at time t. And of course, it says in the elementary calculus, it is shown that all the functions that satisfies this, that is this differential equation, is given by this one. Just like, remember, if you are going to find dP by dt of kp, maybe in order to find the value of P of t, maybe you can write this differential equation like this: dP over P is equal to what? P times of dt, yeah? So upon integrating both sides, this will be what? Ln of absolute value of P, which is equal to PT, yeah? So this will be what? Just like to avoid, to get P, maybe P at time t to mean, P of t will be what? E rise what? E rise something. That's just like upon integrating, it's obvious that we can use what? We can use plus some constant, C, or like, yeah. Therefore, like upon integrating, it will be e the power of, because this could also be written as e raise some constant, yeah, like this. So this will be like e is the power of kt times e the power of c1, and we can write this as some constant c or k, like this. So it is easy that this will be treated as the general formula, the general solution for the differential equation 1.13 to mean. Anyways, don't bother about how are you going to find the general solution for a certain differential equation, okay? We will see it later on in the next sessions. And now just like know that if we have a certain differential equation, it is possible to find the solution to me. Okay, so like one we have considered is simply the general solution. However, we could also be interested in finding the partial solution, that is a particular solution or specific solution to me. The specific solution. In order to find this specific or particular solution, we need to get extra information, okay, beside to the differential equation. For example, for this Malthusian model, we may we may want to know the population of the bacteria at time t is equal to 0 to mean. Therefore, that will be considered as our additional information to solve the specific solution to me. For example, it says if P naught denotes the number of bacteria present at t is equal to 0, which means like P naught means P at time 0, at time not like this, that is t is equal to 0. Then we have what? We have that the initial condition. This will be treated as the initial condition. Now we have this initial condition, and previously we have this general solution P of t, which is like c times let me use my marker, and we have the general solution P of t, which is e the power c times e the power of kt. See, so here we have initial condition, here we have the general solution. Now it will be easy to find what exactly the constant c is. Upon finding the constant c, just we are trying to find the specific solution to me, because when we have c, this will be more of general solution, because c is any number, yeah, any number. However, if we know the initial condition, that is the number of population of the bacteria at the time t is equal to 0, which means it's possible to find exactly what c is. So as you can see it, at p is equal to 0, this will be e the power of 0, 1, so this will be c will be at p at 0. Therefore, instead of c, we are going to use what? P naught, p at 0 to me. P at 0, so this will be what? This will be the particular solution. Or we can say the specific solution. Yeah, so like the advantage of having the particular solution is like we want to get exactly the solution what we are going to model our problem to mean. And of course, if we get this P of t equal to P naught times e the power of kt, when k is a positive constant, that like from this model, we can predict that the bacterial population grows exponentially in time t to mean. When time t goes high, just like the population of bacteria also goes high to mean. That's what is exponentially to mean. And of course, this is consistent with the observation of bacterial population, but this model might not work exactly to other populations, like population species, like people, of people, insects, maybe like aquatic animals like fish, and so on to me. So this works for the bacteria. Here we have another logistic population model, and this logistic population model is like more general, just like corresponds to the case when we assume that there is a constant birth rate. B naught is like the birth rate constant per individual, and that the days rate per individual is proportional to the instantaneous population. Therefore, the resulting first order differential equation will be given this way, and where B naught and D naught are positive constants, which means the Maltesian model that we considered for the population of bacteria could also be like included here, where B naught is K and like D naught will be 0. If we substitute B naught equal to K and D naught equal to 0 here in the logistic population model, you will directly obtain the Maltesian model. And of course, this differential equation could also be written equivalently this way: dp by dt as k times of 1 minus p over c times p, where k is like b naught and c could also be written as b naught over d naught. These are like numbers. Therefore, this is also a certain model, population model domain, which is called the logistic population model. And if we have models like differential equations, if it is like good, there has to be a carrying capacity like this. This carrying capacity is also called the limiting population, and the limiting population, this one is a limiting population, you can say this one, okay, limiting population. Oh, you have it here. I wrote it here. Population. So this limiting population is also called the carrying capacity of the population, and this always represents the maximum population that is sustainable with the given resource. Okay, for example, you can see it here. Now the population is increasing when time is going, also when time is increase. Finally, there is a limit to mean. Okay, it doesn't continue. It doesn't increase like this. No, not well like this. But there is a limiting, which means there is a maximum possible number of population at t goes to infinity to me. So you have to consider this one as t goes to infinity. However, the population will be simply go to a certain number, maybe we can call it star, and this star is called the carry capacity or the limiting population, we can say it. Just like let's consider another model for the Newton's law of cooling. We now build a mathematical model describing the cooling or heating of an object. Suppose that we bring an object into a room. If the temperature, now we have like a certain object and we bring that object into our room. If the temperature of the object is hotter than our room, what do you expect? Of course, the object will begin to cool, yeah, because like our room is colder than the object to me. And further, we might expect that the major factor governing the rate at which the object cools is the temperature difference between the object and what? The object and what? The room to me, yeah? That there has to be what? Temperature difference. Therefore, according to the Newton's law of cooling, it says the rate of change of temperature of an object is proportional to the difference between the temperature of the object and the temperature of the surrounding medium. That is the difference. This is the rate, you see, dt by dt. This T, capital T, is the temperature of the object with respect to time t, and this is minus k times of t minus tm. And of course, this k is what? Must be positive constant. Not only constant, but must be positive. Okay, you can see it. For example, if t is greater than tm, what we are saying, if like the temperature of the object is greater than the temperature of our room, which means like the temperature of the object will getting what? Colder and colder, yeah? Which means like this t minus tm is positive, and upon multiplying by minus of positive number, this will be dt by dt by dt will be what? Less than 0. This shows cooling, yeah? That is cooling. Is cooling, yeah? And if t is less than tm, if t is less than tm, so this will be negative, and negative by negative will be what? Positive. So this will be dt by will be greater than 0, which means now the object is heating, yeah? Why? Because our room is hotter than the object to me. Hotter than the object to me. So this shows that k must be what? Positive constant. It doesn't matter, yeah, positive constant. Okay, let's continue. So just like the general solution for the differential equation that we consider will be t at t will be what? Tm plus c e the power of minus kt. How we obtain this one, we'll see it next time. Okay, just don't bother about the solution. Okay, I will show you how to obtain the solution of the differential equation. As far as you know, integration and differentiation, no problem with finding the solution. Okay, we have many methods of solving the differential equations. Okay, like this. So Newton's law of cooling therefore predicts at t approaches infinity, just like consider this equation. As you can see it here, this one is a general equation, the solution for the Newton's law of cooling. So when t is very high, like when t goes to infinity, as t goes to infinity, this term will go to 0. Therefore, as t goes to infinity, we have what t at t will be what goes to t of the medium, t of the medium. So like this, in both cases, you can see that if like the object, if the temperature of the object is like hotter than that of the medium, at t goes to infinity, the temperature of the object will be what? Reducing, and going down. And finally, we reach where? The limiting. This is the limiting object that we have already considered here. This one is a limiting population or carrying capacity, what we call it, the carrying capacity. Similarly, if you see this in the other way, where we have like a colder object than the medium, then as t goes to infinity, again, we have that t of t will be moving towards Tm. So because this one is colder than the medium, now just like this object should gain what? A temperature. So it is going up, increasing, and finally, when the temperature of the object is equal with the temperature of the medium, just it will stop like this, which means like it will be like similar. So still there is also carrying here, carrying capacity is here in both of. So like this, the Newton's law of cooling, that is a differential equation of the Newton's law of cooling is like nice differential equation, I can say, because of the existence of the carrying capacity. Please go to page 4 and page 6 of your book and see other formulations of the differential equation. There is also examples on the orthogonal trajectory problem, Newton's second law of motion, spring, and so on. Please go and enjoy. This is important course that you should know, especially how to formulate a certain differential equation. Next is basic ideas and terminologies. So suppose we have a certain differential equation, and how are we going to find, how are we like differentiate whether it is linear differential equation or not? So here we have a differential equation that can be written of this form: a naught x times y to the, this one is like the nth derivative, plus a1x times the n minus 1's derivative through nx times y, which is equal to f of x, where this a naught, a1, a2 through an, and of course this f are functions of x only, don't forget, only it says, is called linear differential equation of order n. Why order n? Because of the highest derivative what we have is to the nth derivative, that is order n. And of course such differential equation is linear in y, y prime, y second double prime, y triple prime, and the nth derivative to me. So just like to say it is linear differential equation of order n, just like the coefficients must be of function of x, okay? The coefficients as well as f must be function of x. Otherwise, it's called nonlinear differential equation. Let's see whether these differential equations are linear or nonlinear. Here we have order 3, yeah, because this one is highest. This is 3, order 3. Yeah. Why? Because this one is the highest derivative. This is order 2. This is 2. This one is 1. And the ln x. So let's see the coefficients. The coefficient, this is function of x. It is good. This is also function of x. Nice. Here we have cos x. That's function of x. Ln x is also a function of x, which is our f. Therefore, this is what? Linear differential equation of order 3. because highest order is 3. Is linear differential. Yeah, good. How about this one? Okay, here we have the highest derivative is 1, and the coefficients are functions of x. Here also we have functions of x. That's good. Therefore, we can say that this is linear differential equation of order 1. This is order 1. Linear order 1. Linear differential equation order 1. This one is order 3. How about this? The second examples. We have second derivative. This is cos of y prime minus xy, then equal to e to the power of x squared. This is second order. It is good, but this one is nonlinear. Why nonlinear? Because of this cos y bar. This one. It must be a function of x. We have said it, yeah? Yes, it is here. How about the second? This one is second order. It's good. Is it linear or nonlinear? This is also nonlinear. Because of what? Because of the availability of y squared. Y squared. Therefore, these two later examples are nonlinears. Nonlinear differential equations. The general forms of first and second order differential equation can be written this way. This is a general equation of the first order linear differential equation. Okay, a naught x here, as you said, this one is a1x, which shows function of x and f of x. And similarly for the second order, a naught x, this one is second derivative, a1x, first derivative, a to xy, which is f of x. So this one is second order linear differential equation, second order. This one is first order. This is general equation, okay? So like previously we have seen different differential equations, models of population, like the Malthusian population model, and this was the Malthusian population model. So can we say that this is a linear differential equation? Yes, dp by dt, kp, which is equal to 0. So we can say that this is what? Linear differential equation of first order, p by dt. And this was also Newton's law of cooling. We have also seen this was Newton's law of cooling after rearranging, yeah. So can we say that this is also linear differential equation, dt by dt, kt, ktm. Yeah, this is also good. This is also first order linear differential equation. And the one that we didn't consider but can be used here is the simple harmonic oscillation. Just you can see in the book where I gave you the reading assignment, you will obtain this differential equation of second degree. You can see it here. Second degree, d squared y dt squared, d squared y dt squared plus omega squared y equal to 0 is second order linear differential equation as well. So like go to the simple harmonic oscillator exercise, which is in page 5, I think, or page 6. You will get it. Just like practical examples related to the order and whether it is linear and nonlinear differential equation to me. Therefore, next is about how to get the solution of differential equation. Solution to differential equation, it says a function y that is at least n times differentiable on an interval I is called a solution to the differential equation one-to-one. Just like when to say one-to-one, this is like the general equation that I gave you here is the one-to-one. This is like the linear differential equation of order n. So to say that y is the general solution, or it's called the solution to the differential equation on a certain interval, if what? If we have, if substituting y is equal to f of x, that is the solution, and its derivative, its second derivative, and the nth derivative reduces the differential equation into an identity valid for all x in I, just in this case, we say that this y is equal to f of x is simply satisfies the differential equations. Therefore, it will be treated as the solution to the differential equation. Just it is a matter of substitution as checking, yeah. For example, it says verify that for all constants c1 and c2, this y, which is given as c1 e raised to x plus c2 e raised minus to x is what? Solution to the linear differential equation of this. This is second order linear differential equation, yeah. So what we are going to do is what? We have the function y, and if you consider the differential equation, we have a second order. Therefore, we need to differentiate y derivative and what? Then we have to find second derivative. Upon obtaining the second derivative, we have to substitute here. Then minus 4 times y is already given here. If it gives us 0, which is considered as identity in this case, which means we can say that y is what? The solution to the linear differential equation. If it doesn't give us 0, which means this will not be considered at what? Not a solution. Let's see it. So here we have y, and upon derivative, please remember derivative of exponential function, c1 e raised to x. What's the derivative of this c1 e raised to x? It is 2 times of c1 e raised to x because of the chain rule to x. So this is good. Here also we'll have minus 2 c2 e raised minus to x. That's good. Then we need to differentiate to y's. Why? Because of the differential equation is second order. Therefore, what will be the derivative of y prime? That will be y double prime, and this will be what? 4 times of c1 e raised to x. That's great. Plus minus 2 times minus is what? 4 times of c2 e raised minus to x. Upon taking out 4 as common, this will be c1 e raised to x plus c2 e raised minus to x. Oh, so this will be like this, 4y. Can we say this is 4y? c1 e raised to x plus c2 e raised. Yeah, we can say that y double prime is what? 4y. That's good. Therefore, if we substitute here, this is what? 4y minus 4y. That's 0. Oh, that's great. So we can shorten it like this. That's good. Which shows that y is what? The solution to this differential equation. You see, like they substitute, it substitutes y double prime is this one, minus this is 0. So in this case, we can say that for all x in the interval, in the set of real number, or we can say, or in the interval minus infinity to infinity, it's like it works that the function is really the solution to the differential equation given. And if we have solution, it could be like 2 types of solution. One could be the general solution, and the other could be the particular solution. We have discussed earlier, just like to see it in detail here. A solution to an nth order differential equation of an interval I is called the general solution on I, if it satisfies the following condition. When we say general solution, the solution contains n constants c1 through cn. That makes it like more general. And all solutions to the differential equation can be obtained by assigning appropriate values of the constants. But not all as a necessary, like not all differential equations have general solution. For example, if you consider this differential equation, its general solution is simply the constant function 1, because if you derivate y prime of x, that is 0. So this will be 0 squared, 0 plus 1 minus 1 is 0, 0 squared 0. So this will be 0. And this will be considered as a general solution. Therefore, we can say as a remark that not all differential equations have general solution. And for those differential equations that have general solution, it must satisfy these two conditions. Okay, let's see this example. Determine the general solution to the differential equation. This one, just like it's not difficult to find the general solution for such simple differential equation where we have second order. Y double prime is 18 cos 3x. So like upon integrating both sides, this and this, yes, it will be y double y prime, and the integration of 18 cos 3x will be like 6 sine 3x plus some constant c1, and of course upon integrating this one both sides, this will be what? This will be y at x, and this will be minus 2 cos 3x plus the integration of c1 dx will be c1x plus some constant c2. So you can see that this will be treated as what? The general solution for the differential equation given here to me. This is how to find, and all solutions of this differential equation are of the form this one. And why we say that it is general solution? Because it consists constant c1 and c2, where of course c1 and c2 are like in a certain set of real numbers to me. So this will be considered that one general solution. Now, when we come to the initial value problem means what? It is a differential equation along with a condition. Initial value problem means what? This is differential equation plus some condition. So the condition could be initial value. Okay, initial values, maybe. Yeah. So like as discussed previously, the unique specification, that is like unique specification. We need like unique solution, specific solution of an applied problem, which requires more than just a differential equation. So in this case, we must also give appropriate auxiliary conditions that characterize the problem under investigation, just like of particular interest to us in the case of initial value problem defined for the nth order differential equation. Just like here, we need to find what unique specification like this. For example, this one is general solution. However, yes, we might be interested to find what C1 and C2 is based on like the applied problem what we have, which leads us to find unique solution or unique specification. So like initial value problem is like differential equation along with a certain initial condition. So it says definition, an nth order differential equation together with n auxiliary conditions. You see, we have differential equation and we have auxiliary conditions. This one is condition, y at x naught is y naught, y prime of at x naught is y1, y double prime of x naught is y2, and so on. And this one is the n's minus 1's derivative of y at x naught is yn minus 1, where this y naught, y1 through yn minus 1 are constants, and is called what? Initial value problem. Just like to be more clear here, consider this one. This is what? The differential equation. And these are what? The auxiliary conditions. Okay. Because this one is second order, we have what? Y naught at 1, y naught, and y prime at 0. You see, we have to have what? Auxiliary conditions up to what? Up to the n's minus 1 derivative for what? For the nth order differential equation. So this one is second order differential equation, and the auxiliary conditions what we have is up to what? N minus 1, 2 minus 1. That is up to first derivative to me. So just like, let's see this example, and it will be more clear for you. It says solve the initial value problem. Here we have initial value problem, and we are going to find the solution of this one. I think we have solved this one, 18 cos 3x. That was the question. Yes, so we have general solution already. So we'll come up from this. We have general solution, and now by using the auxiliary condition, we are going to determine C1 and C2. That's all. Okay. So it says from the above example that we have seen, this is a general solution. That's correct. Now we should substitute the auxiliary conditions. We have two auxiliary conditions. One is y naught, that is y at 0 is 1, and y prime at 0 is 4. So by using this, just like we will be bearing like C1 and C0, C1, C2. So y at 0 is 1, if and only if what? 1 minus 2 plus C2 is what? Like this. Y naught is 0, which means like when x is 0, y at 0 to me is equal to what? This will be 0, so this will be minus 2, because cos 0 is 1, plus C1 times 0 is 0, this will be C2. And like y at 0 is what? 1, so this is correct. So from this we can obtain C2 is what? 3. Yeah, similarly, from the first derivative of this general solution, the first derivative of y is what? Minus 6, because this will be minus of 3, this will be 6 cos sine 3x plus x, and I mean C1, finished. Now let's substitute y prime at 0 is what? 6 times sine 0 is 0 plus C1. But y prime at 0 is what? It is 4. Therefore, from this, we have what? C1 is simply 4. Therefore, just like we are saying that the specific solution or the particular solution is like yx, this one is like C1, and this one was what? C2 to me. Is that? No. C1 is what? C1 is 4, so this one is C1, and of course C2 is 3, this one is C2. So we are able to find what? The particular solution. We are able to investigate the exact values of C1 and C2 based on the auxiliary conditions given here to me, based on the auxiliary conditions given here. So this is how to find, just like how to formulate differential equation, how to check whether a certain function is the solution of the given differential equation or not, and like how to find the particular solution of a certain nth order differential equation, given that the auxiliary conditions are there. So just like I will give you like exercise related to this class, and then answers will also be given as we do always. All the best.